Well, thank you for your patience, everyone, and welcome. Thank you for taking your time today to attend our webinar, the SBA-5 CO2 Gas Analyzer, a key component for researchers monitoring and understanding degassing processes at active volcano sites. Just a bit about the format. Dr. Moor will present first, followed by Dr. Stix, and then Jessica Salas. We ask that you remain on mute for the entirety of the presentation, and please place any questions you have in the chat, and we'll do our best to address all of them. For any that we don't get to, we'll be sure to email you a response personally following the presentation. The presentation will be recorded and will be shared at a later date via a link I'll send to you in an email. So we'll get started. First, I'd like to introduce each of our presenters to you. Our first presenter is Dr. Maarten de Moor. He's a volcanologist focusing on using gas geochemistry to understand volcanic processes and evaluate volcanic activity. He's based at the Observatory of Volcanology and Seismology in Costa Rica at the National University and uses in situ instrumentation at active volcanoes to show that significant short-term variations in key gas ratios accompany and in some cases precede eruptive activity. Real-time gas data thus provide insights into eruptive processes and show great potential for forecasting dangerous volcanic eruptions. Next, we'll have Dr. John Stix. He's a professor of volcanology at McGill University in Montreal, Canada, and he holds the William Dawson Chair in Geology. He has worked on active volcanic systems since 1989 with a focus on volcanic gases, supervolcanoes, which I think is a really cool word, and subsurface magma plumbing systems. He's the past editor-in-chief of the Bulletin of Volcanology, which is the premier journal in the field, and he and his group are continually searching for novel and exciting ways to study active volcanoes and their impacts. Last but certainly not least, we have Jessica Salas. Jessica is a chemist and a master's candidate in the Department of Earth and Planetary Sciences at McGill University. Prior to joining McGill, she was a research assistant at the Costa Rican Volcano Observatory, where she became interested in geochemical research, monitoring volcanic activity, and science communication. Currently, she works with Dr. Stix and Dr. de Moor to design a new version of the MultiGAS, which is an instrument capable of real-time field measurements of volcanic gas concentration, which you'll learn more about today. As I said, please remain on mute and place any questions you have in the chat, and I'll now hand the floor over to Dr. de Moor.
All right, thank you very much for the introduction. Can you guys hear me okay?
Yes.
Okay, excellent. Let's see. And you can see the screen? Mm-hmm. Okay. All right, well, thanks again for the invitation to give this talk. Today we're going to be talking about, this is not the right presentation, excuse me. Let's see, this is the right presentation. There we go. So today we're going to be talking to you about using the PP Systems SBA-5 Gas Analyzer and some of the applications that we've developed in the last year. This photo in the background was taken from a drone at Pois Volcano during the 2017 eruptive phase. And you can see that there is a lake here in the crater, and we have this huge plume of steam that also contains ash being emitted from the crater. And we flew this drone into the gas plume to measure gas ratios, which is what the application that John's going to be talking to us a little bit more about today. I'm going to be focusing on the MultiGAS instrument, which is too big to be put on a drone. This is an instrument that was first developed in Italy and in Japan, at least a prototype, I would say, of this instrument. And what we have here is essentially the SBA-5 over here in the bottom of the box. Oops. In the bottom of the box there, which is analyzing CO2 and water concentrations in the gas, and also comes with a pump, which basically drives this whole instrument. So the sample is sucked in through these tubes on the left, the Plume gas, and it passes through the instrument to an SO2 and H2S sensor, and then to the SBA-5. The data is recorded on a Campbell CR6 data logger. And we have a radio over here which transmits the data directly to obviously Corey and publishes the data on the web in real time. The permanent station looks like this. So that box over there is mounted on a post here. We've got the antenna, big solar panel, and in the background we have the vent. So this is located about 300 meters from the active vent that drives the eruptions. And this instrument is designed to have a small profile, and that's because during eruptions, the smaller the box is, the less chance it's gonna be hit by volcanic bombs, like rocks being thrown out of the crater. The way that this instrument works, so these are some data produced in a lab experiment, and so on the x-axis we have time, and on the left y-axis we have CO2 concentration, and on the right axis we have SO2 concentration. The first big square peak here is attaching a bag of standard gas containing both CO2 and SO2 to the instrument. And we can see here that the peak for CO2 is really nice and square, whereas the SO2 sensor has a slightly slower response than the CO2 analyzer. So this is how we calibrate the instrument, is by using these standard gases. These spiky peaks over here are where we're doing a dynamic mixing experiment. So basically pulses of gas that are from the tank that are mixing with the air, and we can see that these CO2 and SO2 peaks correlate. And we have two standards here, one that has a lot more CO2, so up to 1,900 ppm CO2, and then we have this second standard which has much lower CO2 concentrations. And this is what's so important about the SBA-5, is that even with low CO2 concentrations in the plume, we can get a very good correlation between CO2 and SO2. So what we can see here is that this linear regression through these data points over here faithfully reproduces the gas ratio measured in the plume. The programming of the system, so the system is not running 24/7. It turns on 3 times a day and starts this sequence. So first we have a warm-up procedure. So only if the battery is sufficiently charged, then the sequence starts. And the first thing to power on is the PP Systems SBA-5. Then after 5 minutes or so, the power to the electrochemical sensors, SO2 and H2S sensors, is turned on. This is just to warm up and stabilize the background. Then after a certain amount of time, this time actually varies depending on where we put the instrument, because our higher volcanoes, the SBA-5 takes longer to warm up. So we have to adjust this based on where the instrument is. But after this warm-up period, then it starts collecting data and calculating real-time gas ratios. After about 30 minutes of analysis, then the instrument stops, turns on the power to the radio, and sends the data to our servers and publishes the data on the web. And then after that happens, then the power turns off. And you can modify the schedule that the instrument turns on and off, but most of our instruments are configured to do an analysis at 10 a.m., 2 p.m., and 1 a.m. So this equates to about 4 hours of charge during daylight hours for each session. And if the battery voltage is less than 11 volts, then this whole program is modified so it'll only run once a day. And the reason for that is because this is quite a frequent occurrence. Okay, so this is at Pois Volcano, a small ash eruption, and the solar panel gets completely covered with ash. This is a rainy country, so eventually the rain will wash the ash off these solar panels, but we want to keep analyzing or getting some data at least from the station even while it's covered with ash. which is why if the battery voltage drops below a certain level, then it switches to just one analysis per day until the solar panel is cleaned off and the battery starts charging again. So as an example of the application and the power of these data, we have a really nice case from Pois Volcano, and we've seen significant changes there, particularly an extremely good example in 2017. So this photo on the top shows the case at what the crater looked like in late 2016, late 2000 or early 2017, which with a stable lake and not much, well, no eruptive activity. This period was associated with low SO2 CO2 ratios, and notice that this y-axis is logarithmic. So in April, the beginning of April 2017, we got reports. This is a photo taken by a tourist showing some kind of activity occurring at the edge of the lake. And at the same time, we saw a drastic increase in this CO2 SO2 ratio. And this situation, this ramp up in the SO2 CO2 ratio occurred right before the largest eruption that's happened at Pois since the 1950s. And the data, this eruption took out the MultiGAS station that we had. So after this, the instrument was destroyed, then we started using drones to measure the SO2 CO2 ratio, as was shown in this photo over here. And we can see we recorded the system stabilizing again after the eruption. In mid to late 2017, this whole lake was evaporated by this injection of heat and magma into the system. And when the lake was completely dissipated, it revealed these amazing sulfur vents that were underwater, submerged in the lake, which is feeding this acid lake system. And then once the situation had calmed down enough, and once we were pretty confident that the volcano was safe to approach, then we installed this MultiGAS system, and we can see here that we started collecting data. During this prototype phase, we had some issues with data, with basically like the robustness of the station, but those are now improved, which is shown over here. So since 2017, we've greatly improved the data acquisition. So far fewer gaps in the data. But we still see these large variations in SO2 CO2 ratio. And so these peaks here, the highest values of SO2 CO2 are associated with eruptive periods. This was a phreatomagmatic eruption that occurred in 2019, right here at the end of September. And these periods where we see very low SO2 CO2 ratios is when there's influx of meteoric water into the system. And so we've been able to record the reformation of the lake and the effects that this has on the gas ratios. So what we can see here is that these low SO2 CO2 ratios are associated with the formation of the lake, and we attribute these low ratios to scrubbing or reaction of SO2 with meteoric water to form sulfuric acid. And so under these conditions, CO2 is not reactive with water because it's so acid, and so this ratio goes down. And that is my part of the talk.
Thank you. And we're going to hold our questions until the end. And Dr. Stix, would you like to jump in next?
Perfect. Okay, let me just share my screen. Perfect. So Maarten showed some really crucial drone data that what he collected in spring of summer 2017 when the permanent station Pois was destroyed. There was really no other way to collect data at that time because of the lack of because of the lack of the permanent station, and B, because there was a high degree of danger and risk in terms of going into the crater and taking samples in terms of sending people in. So the drone really was truly it was in the right place at the right time. So I just want to give you some details about how we've been using drones, and this is something that's evolving quickly because things change and we can make improvements and so forth. So it's a super exciting field to be in right now. So this is a great photo then showing another volcano in Costa Rica called Turrialba, which we've all worked on. We're all collaborating on Turrialba in many different ways. And this is a photograph of a drone flying in 2017 in April into the Plume. So the Plume is located right here. Let me show you here. The Plume is actually right here. It's this white gas right here. And this is just all down here. This is just ash that's been put into the air as the drone's just taken off. So it's a very ashy and dirty environment, but the drones seem to operate really quite well, even in these dirty environments. And here's another photograph at the summit of Turrialba, where we're actually flying the drone into the high concentration gas located right here. And actually you can't see the crater because it's obscured by the gas. And this is the takeoff point right here. And so the takeoff point, let me just show you, these are three different views of the traverses we did at Turrialba. So the takeoff point is located right here. And so we flew the drone into the gas plume to the west and then back like that, okay? And the different colors here shows the different concentrations of not CO2, but SO2 right here. SO2 is a very easy gas to measure in many ways. And it's an important reference gas for us in terms of degassing volcanoes. So we do SO2 at the same time as we do CO2. And I'll show you why in a second. So let me just show you some information then about, so you can see over here that the high concentrations are to the west because the plume is blowing essentially in this direction. So the highest concentrations are located right about here, the reds here. Okay, and so to measure the SO2, Maarten very cleverly built an instrument mounted on the drone here on the S1000 octocopter, and so it flies actually under the plume, collecting SO2 data from the plume itself. So the first thing is we need from these plumes is SO2 data and SO2 fluxes. And these are some traverses. Let's look at Turrialba right here. Here are two traverses through the underneath the plume of Turrialba. And so here we're on the edges of the plume. We're outside the plume here. We're outside the plume here. And then as the octocopter flies under the plume, okay, in both directions. So the red traverse is one direction and the blue traverse is the return. You can see the SO2 concentrations located on the vertical axis go up and then they go down. So we can get very nice traverse data from SO2 and SO2 fluxes. So we're aiming to get SO2, the flux of SO2, the emissions of SO2 from the volcano. So now here we have the octocopter on the summit of Turrialba. Here's the degassing plume from the crater above us. Okay, and we have two MultiGAS instruments mounted on this octocopter. So one system is built by our colleagues at the University of Costa Rica called a MiniGAS, and then this is the instrument built by McGill called a MicroGAS. And the two instruments really, the principles are exactly the same, and despite the fact that we built these in two very sort of different ways. So if you look at the MiniGAS, here's the components of the MiniGAS. The CO2 sensor, the SBA-5 instrument is located right here, and there's also an SO2 electrochemical cell and an H2S electrochemical cell. And this instrument is very nice because we are actually able to see the gas concentrations in real time as the drone is flying. And this other instrument, the one built at McGill, it collects data and the data is downloaded afterwards. So it's not a real-time system, it's a system that collects the data, and then we collect the data, then we download the data afterwards. So let me just show you some of the core components right here. So here is the SBA-5 right here. It's the board, which is a little buried underneath all the bits and pieces. And I'll have you note the elegant Tupperware container into which all this material is contained. And so the two so here's the SBA-5 for CO2 and also water vapor as well, which is really great, very useful for us. And then the two electrochemical cells are located right here. There's one cell here, and there's another one underneath this switch panel located right here. And then the data are recorded on mini data loggers, very high resolution mini data loggers located right here. And there's a small battery, a small lithium ion battery here. And then here's the scrubber. Here's the zero scrubber with soda lime, which is needed for the SBA-5 to calibrate it and to zero it, a really important component of this sensor. Okay. And then let's go to Masaya now. Here's Masaya. Here's a photograph of Masaya volcano in Nicaragua. And the active crater is just down here. Okay, it's called Santiago. And here's the beautiful high concentration gas plume that's blowing off from Santiago, which was in 2017. And a beautiful photo of the lava lake at Masaya. Masaya has this very, very special, very, very vigorous lava lake. Which is currently present. It's not always there at Masaya, but right now it has been, and it's just been an amazing place to do research over the past few years. And here are some data then from Masaya, and what we're looking at. These are the MultiGAS data then from Masaya, and we're looking at this very key ratio, the CO2 SO2 ratio. So CO2 simply plotted here, SO2 simply plotted here, and showing this beautiful correlation of this data collected with the SBA-5 for the CO2 and the electrochemical cells for the SO2. The very good correlation and this key ratio right here. And so if we have SO2 fluxes, okay, measured by the DROAS, which I showed you at the beginning, and the CO2 SO2 ratio, we can also calculate the CO2 fluxes coming from the volcano. And that's a key measurement. That is really an important measurement, both in terms of volcano monitoring and also in terms of global emissions of CO2 and SO2 from volcanoes worldwide. And down below here, we have another great correlation between water vapor, and this is water measured on the SBA-5. We actually measured it two ways. We measured it on the SBA-5 using the water vapor component of the SBA-5, and we also had a separate relative humidity measurement instrument, and they corresponded very, very well. So here we have the H2O SO2 ratio, another beautiful correlation, and so we can get water fluxes also from these volcanoes. So it's really amazing amount of data. So the SBA-5, I just want to summarize why this instrument is so great on drones for all sorts of applications, not just volcanology. It's very, very accurate. It's a very, very accurate instrument, and it can measure CO2 at very high precision, around a ppm, maybe a ppm or two. And with a bit of averaging, I think you can go easily to sub-ppm precision with this instrument. It measures water vapor, has a pump built in, so the pump is actually driving the entire system. The SBA-5 is not just a sensor, but it's actually the motor, the pump that fluxes the gas through the MultiGAS system. And the other great thing for drones is that it is pressure and temperature compensated. So the drone goes up, the drone goes down, the drone goes into warm air, then it goes up and it gets colder. But that instrument is temperature compensated. So those issues are essentially easily resolved by the instrument itself. And finally, last but not least, this instrument weighs 200 grams. And I remember, I'll just tell you one short story before I turn it over to Jessica. I remember snooping around at the AGU meeting in fall 2014 or 15. I can't remember exactly. And I'm pretty sure I met Mike Doyle of PP Systems at the meeting, and there was an SBA-5 sitting on the table. And I go, wow, that's very interesting. And he told me all about it, and I got really excited. Okay, that's the end of my presentation, and I'll turn it over to Jessica. Let me just stop sharing.
Thank you very much. Jessica, if you'd like to go next, and then we'll handle some questions after.
Hello, can everybody hear me? Okay. So thanks again for having us. I'm going to talk a little bit about the new version of the MultiGAS that the three of us are working on right now. So our plan is to build a new MultiGAS station, including a methane sensor for the first time ever in this instrument. So in my talk, I'm gonna go a little bit with the motivation of why we're doing this and a little bit of the design that we already have for the instrument, as well as some of lab results that we have. And I'm gonna start pointing out some of the differences that this MultiGAS station or this new version that we are designing, the difference with Maarten, the one that Maarten just was explaining to us. So first of all, we're not planning to install this station in the summit of a volcano. We're planning to install it in the hydrothermal system. It means like in the hot springs or some kilometers away from the summit of the volcano. And this is because the methane concentration is going to be higher in the hydrothermal system. So maybe let's go to this figure here, where we can see here at the top is my hydrothermal system. And as I said before, here, the methane concentration is going to be higher. But underneath the volcano, the CO2 concentration is going to be higher. So therefore, it is expected that when magmatic fluids are going to go up to the surface, the CO2 methane ratio is going to increase. So this increment in the CO2 methane concentration ratio is the one that we want to monitor continuously and in real time. This parameter was found by an Italian researcher in 2009, and he proved that it's a good parameter and a good tool to potentially even forecast an eruption. But what we're planning to do different is that we're going to do it in real time and taking measurements continuously. And it's something that no one has done before from our knowledge. So this, we're able to do it due to the new technology that we have, of course, as the PP system, as well as new technology to measure methane. Also, we're planning to do this as a safer way for us as researchers, as well as for the instruments. As Maarten was saying before, some bad experiments have happened in the past because of the eruptions in the volcano. So now we want to step a little bit away and from the dangerous part, hopefully have even as good results as we're having. So here is the diagram of the instrument, the one that we're designing so far. So first of all, we have a data logger, as Maarten already explained. This data logger is powered by the small battery of 12 volts because there's all the four of the sensors, as well as the data logger, they're all low consumption energy. So here we have the PP system that is going to be at the beginning of the flow, because the pump is gonna drive the gas through the sensors. So first of all, the gas is gonna get in, it's gonna find a filter that is gonna avoid some particles, small particles to get in our system. After the PP system is gonna go to this methane sensor, then the H2S sensor, and after that, the H2 sensor. Here we have a real picture of how it is actually looking right now. Here, the PP system that I'm using in these instruments goes from 0 ppm to 100,000 ppm. So the range is really great, but we're gonna see later that the resolution is really good for all of the whole range. So then here, this is the small methane sensor, the H2 sensor, and the H2S sensor and H2 sensor. And here we have some of the lab results. So here what I was trying to do was to find a correlation between cavity ring down spectrometer as Picarro. Picarro can measure water, CO2, and methane. So I did some lab experiments where I did gas mixes in bags. So each of these points in the scale are different bags. And each bag I measured with the PP system and with the Picarro at the same time. And we can see that this linear regression is really good for both of us, probably assuring us the accuracy of the PP system to measure the CO2. And here I just add the one for the CO2 sensor that we're using, which is really accurate as well with Picarro. And here's some more of the experiments that we did, where we did not find any cross interference. In this experiment, I'm going to try to explain it a little bit. I was adding methane. I was increasing the methane concentration to 0 CO2. So we were trying to find any interference. So here we can see that even when we got to 250 ppm of methane, we were not able to find any interference in the CO2. So the PP system was not getting confused at measuring methane, which is great for where we wanted. And in this other one, I did the same experiment, as you can see here in my y-axis, from 0 to 100,000 ppm of CO2. I added all the way from 0 to here. And again, the methane sensor was always pretty stable and did not suffer any interference, which is great for what we wanted. And later on, we also did the same experiments, but this time with H2S, and we did not detect any cross interference with methane or CO2. And with the previous, the most recent lab experiments, we find that we are able to highly accurately determine the CO2 methane ratios. That is the one that we were looking for. So these findings are really exciting. We're looking forward to be able to install this station and go to the field again when things go back to the normal, if that happens sometime soon. So that's where we are in this project, and we have high hopes that it's gonna work great and that we're gonna find great results with it. And this is all from my side.
Oh, thank you very much. And thank you to all of you, Dr. Moor, Dr. Stix, and Jessica. We're going to open it up now to some questions if anybody has any. And Tim, do you want to sort of take a look through and feed the questions in?
Yeah, I've got them now, Carrie.
Okay, great.
So the first question, again, well, first, great presentations, and thank you guys very much.
That's very good.
So the first question we have is, do you use the relative humidity sensor? And does relative humidity influence the CO2 measurements or help characterize the plume? We can pose that to maybe John.
So could you say the question again?
Okay. So do you use the relative humidity sensor? I think you've answered the question as yes, but do you use the relative humidity sensor, and does the relative humidity influence either the CO2 measurement or help characterize the plume?
Okay, so yeah, so we do use the relative humidity sensor to measure. So this is a difficult measurement because the humidity can be so variable in this kind of environment, not only in the volcanic plume, but also in the surrounding ambient environment. So it's a much more difficult measurement to make well compared to the CO2 and the SO2 measurements. So you really have to look. So there's already a very high background of water vapor present in these tropical volcanoes, and so you really have to look around for peaks, for water peaks that are clearly related to the plume and that clearly correlate to increased CO2 and increased SO2. So I'd say for every 10 good peaks of CO2 and SO2 in a volcanic plume, there's maybe 1 or 2 H2O peaks, just because there's so much heterogeneity and variability, and much of the stuff we just can't use. But some we definitely can use, and the stuff that we can use, the peaks that we can use, are reproducible. It's really great to see. The ratios are relatively similar, and so for the second part of the question, to answer the second part of the question, no, the variability in water vapor does not seem to affect the CO2 measurements. The CO2, I mean, this, if it's a completely rainy or saturated or intensely wet system, yeah, maybe at that point. But under the conditions we've been working, it has not been, variability of water vapor has not proved to be an impediment in terms of making CO2 measurements. Maybe you can say something, Maarten, about the ground-based measurements, which are also intensely humid.
Yeah, I mean, yeah, I completely agree with what John said. In Costa Rica, it's so wet that oftentimes we don't get any good like water to CO2 or water to SO2 ratios. But when the weather is really dry, then we can see much better correlations between SO2 and water. But yeah, so in terms of monitoring with permanent stations, it's not too useful just because here it's so wet. I think that in other volcanoes in drier places like in Italy, it's a lot more useful.
Great, thank you guys. We've got another question here. Can you turn the device on and off remotely? And how much SO2 can the lake dissolve? And is the SO2 data during meteoric water SO2 interaction simply the indissoluble or undissolved SO2?
Those are great questions. So yes, I can. So from my desk here, I can start the MultiGAS system in real time. Actually, this weekend, as an example, there at Turrialba volcano, some tourists illegally went to the crater, and one of them got hurt, and they had to send in like a rescue team to go in there, and they were worried about the gas. So I was sitting there turning on the instrument, sequentially, so that we can have real-time data analysis during the whole time of the rescue mission. So that aspect is really cool. And then the other question about the SO2 absorption, that's a great question, and it's something that we still are trying to get a good handle on. But basically, what we think is happening is that when we have big rain events, then we can see the meteoric water streaming into the crater, and we can see that SO2 is being dissolved, and because the SO2 CO2 ratio goes down. But after a while, then the SO2 CO2 ratio goes up again, but there's still a lake there. So what we think is that the lake is getting saturated, or is becoming so acidified that the SO2 is basically just streaming straight through the lake.
All right, terrific. For the use of the SBA-5 in the static MultiGAS system, how often do you have to change out the soda line?
That's another good question. I actually don't know, because I haven't I haven't noticed that there have been any issues with the zero. So what I do, just to try to have a little bit more faith in that, is the tubes that come with the SBA-5, I cut them in half and I add an extra piece of silicon tubing between them, so that I can get more volume of the soda lime in there.
Right.
And I change those out about every 6 months. So seems to be working fine. You guys should probably know better than me about that. Maybe I should be doing it more often.
Well, we can certainly look into larger tubes, that's for sure. But yeah, that's something we could probably look at as well. And a question for Jessica. How did you decide whether to put the SBA-5 first in the sequence, pushing the gas with the pump to the methane and other sensors, or at the end and pulling the gas through?
Well, thanks for the question. And we designed it like that so that the pump help us to put the gas into the system, and then to drive the gas all over the other sensors. So that's why the pump in the PP system goes first.
Mm-hmm. Okay, great. Does anyone else have any other questions? Well, I don't see any other questions coming up. So Carrie, you want to take over?
I couldn't unmute. Yeah, so first, we really want to thank Dr. Moor, Dr. Stix, and Ms. Salas for their time today and for sharing their fascinating research with us. We very much appreciate it. And if someone does have a question they think of later, please don't hesitate to email me directly, and I'll be sure to get your question answered for you. That's it for this webinar, and keep checking back to the website for new webinars in the future. And thank you again for your time. Have a great day.
Thank you.
Thank you.
Take care.
Thank you.
Thank you,
Bye-bye.
everyone.
Bye.
Thank you for attending this webinar. To learn more about how the SBA-5 CO2 Gas Analyzer can enhance your research experience, visit ppsystems.com.